If you've been following this channel, you know I spend most of my time looking up, tracking comets like 3I Atlas, exploring the mysteries of deep space. But today, I need to bring your attention back down to Earth. Not because space has become less interesting, but because our own planet is currently doing something so extraordinary, so fundamentally significant, that I cannot in good conscience ignore it. Right now, as you watch this, the magnetic North Pole is not just drifting as it has for centuries. It is racing across the Arctic at over 50 kilometers per year, abandoning the Canadian territories where it has resided for as long as we've been mapping it and sprinting towards Siberia with a speed and determination that has caught the entire geophysics community by surprise. We are witnessing the primary navigational marker of our planet undergo a transformation that is rewriting the fundamental coordinates of our world. This is not a distant cosmic event. This is happening 3,000 kilometers beneath your feet right now. For hundreds of years, the movement of the magnetic North Pole was a sluggish affair. Since the late 16th century, when explorers and scientists first began to track its position with any reliability, the pole wandered within a confined region of the Arctic. It moved certainly, but it moved slowly, drifting perhaps 10 or 15 kilometers a year. It was a predictable, manageable variable in the complex equation of planetary navigation. But something shifted in the deep machinery of the Earth during the mid-20th century. The drift began to pick up speed. By the turn of the millennium, specifically the early 2000s, that slow meander had transformed into a sprint. The pole began moving at more than 50 kilometers every single year. This acceleration is unprecedented in the modern record. We are seeing the pole cover more distance in a single year than it used to cover in a decade. Satellite data, ground-based magnetometers, and the updated World Magnetic Model all confirm this undeniable trend. The pole is no longer behaving the way it did for the past 4 centuries. It has broken free of its historical roaming grounds in northern Canada and is crossing the international dateline. This is not a theoretical prediction for the future. It is a measurable event happening at this very second. The trajectory is less predictable than ever before. We used to be able to forecast the pole's position with high accuracy for years in advance. Now, the accelerating changes require us to update the World Magnetic Model more frequently, just to keep commercial aviation and military navigation systems accurate. If this is the kind of deep dive analysis into planetary changes that you value, make sure you subscribe to the channel so you do not miss our future reports on Earth sciences and space weather. The sheer speed of this movement suggests a significant change in the underlying forces driving it. We are not just looking at a surface phenomenon. The magnetic field is the external expression of deep internal processes, and a 50 km per year shift is a symptom of turbulence deep below. It suggests that the molten iron currents in the outer core, which generate the field, are undergoing a shift in their flow patterns. We are seeing the result of a planetary hydromagnetic struggle where jets of liquid iron are pushing magnetic flux lobes in new directions. The result is this rapid tug-of-war that is pulling the pole toward Russia. This movement is happening alongside a broader, perhaps even more significant, trend, the global weakening of the field itself. While the pole races across the Arctic, the overall intensity of the magnetic shield protecting Earth is dropping. Over the last 2 centuries, the strength of the magnetic dipole has decreased by nearly 10%. On the scale of human life, 10% might seem like a manageable decline, but in planetary terms, it is a rapid descent. This weakening is not uniform across the globe. It is patchy, irregular, and complex, but the overall trend line is downwards. The magnetic North Pole is the most visible, trackable symbol of this change. It is the needle on the dashboard telling us that the engine is running differently. But why is it accelerating now? Why, after centuries of relative stability, has the system decided to ramp up its activity? The answers lie in the chaotic physics of the geodynamo, the self-sustaining generator inside the Earth. We are observing a system that is far from equilibrium. The old assumption that the Earth is a static, unchanging rock is being dismantled by the data we collect every day. The planet is active. Its magnetic personality is volatile. What is particularly striking is the unidirectional nature of this current shift. It is not wobbling back and forth. It is heading in a straight line, almost as if it is being drawn by a new magnetic attractor forming beneath Siberia. This has led to speculation about whether we are seeing a temporary excursion or the beginning of a larger event. But we must stick to the data we have right now, and the data says the pole is fast. It is erratic, and it is moving away from the Western Hemisphere. The implications of this are immediate for navigation. Compasses in the far north are becoming unreliable. Airport runways, which are numbered based on their magnetic heading, have had to be renamed and repainted as the magnetic direction shifts. This is a real-world cost of a geological process. We are adjusting our infrastructure to match the shifting mood of the planet's core. As we track this racing pole, we must also look at where the field is failing most dramatically. While the North Pole's movement is about direction, there is another phenomenon that is about pure strength, or the lack thereof. There is a region on the planet where the field is not just weakening generally, but collapsing locally. A place where the shield is growing so thin that radiation from space is already punching through. This is where the story moves from a navigational curiosity to a potential hazard for our technology. The accelerating drift of the North Pole is just the opening act. The second act is taking place thousands of kilometers away over the southern hemisphere, where a vast, invisible bruise is spreading across the magnetic field. This brings us to the most concerning anomaly on the map, a growing weakness that scientists are watching with increasing focus. As we established, the North Pole is racing toward Siberia. But while that high-speed migration captures headlines, a far more ominous development is unfolding quietly over the South Atlantic Ocean. This is the South Atlantic Anomaly. It is a vast region where Earth's magnetic field is significantly weaker than anywhere else on the planet. Imagine the magnetic field as a protective bubble surrounding the Earth. In most places, this bubble is thick and resilient. But over South America and the southern Atlantic Ocean, there is a dent. The bubble is thin, stretched, and fragile, and the data confirms this dent is deepening and expanding westward. The South Atlantic Anomaly is often referred to as a pothole in space or a breach in the shield. In this specific zone, the intensity of the magnetic field has dropped so low that it allows the inner Van Allen radiation belt to dip dangerously close to the Earth's surface. Normally, these belts of trapped energetic particles are held at a safe distance. But here, because the magnetic grip is weak, the radiation descends. This allows charged particles from the Sun and cosmic rays from deep space to penetrate to altitudes where our satellites orbit. This is not a theoretical problem for the distant future. It is happening now. Satellites that pass through this region are bombarded by higher levels of radiation than they were designed to withstand. We see regular reports of malfunctions, electronic glitches, and sensor failures. Specifically, when spacecraft traverse this zone, computers on board reset unexpectedly. Data becomes corrupted. Even the Hubble Space Telescope, one of our most sophisticated instruments, is forced to temporarily shut down its sensitive sensors when it passes through the anomaly to prevent radiation damage. The International Space Station, which also orbits through this region, requires extra shielding to protect astronauts from the increased radiation exposure. What is truly concerning for geophysicists is that the anomaly is growing. It is not a static feature. Over the last few decades, it has expanded in size and drifted westward. Recent observations suggest something even more complex is occurring. The anomaly appears to be splitting. New data indicates that the single large region of weakness may be dividing into two separate centers of minimum intensity. This bifurcation suggests that the underlying processes in the core are becoming even more complex and turbulent. We are not just seeing a simple fading of the field. We are seeing a structural reorganization of the magnetic landscape. I want to pause here and ask you, had you heard about this dent in the magnetic field before today? Let me know in the comments below if this specific anomaly is new to you. The weakening we see in the South Atlantic is the most intense example of the global trend we discussed earlier. Remember that 10% global decline? A huge portion of that drop is concentrated right here. This region acts as a window into what a low-field world looks like. It is a test lab for magnetic vulnerability. If the global field were to continue weakening, the conditions we see in the South Atlantic anomaly could become more common across other parts of the planet. Why is this happening here? The anomaly is thought to be caused by a patch of reverse polarity flux in the outer core beneath this region. Essentially, deep under the South Atlantic, there is a swirl of liquid iron that is generating a magnetic field pointing in the opposite direction to the rest of the planet. This reverse field works against the main field, canceling it out and creating this weak spot. It is like having a strong current in a river and then a smaller swirling eddy flowing upstream. The two forces fight each other, and the result is a patch of turbulence and weakness. This reverse flux patch is growing. It is fed by the changing flows of the geodynamo. As this patch expands, the anomaly deepens. Some models suggest it will continue to widen across the southern hemisphere in the coming years. This has direct implications for the future of satellite constellations. As we launch more and more mega-constellations for internet and communications, tens of thousands of satellites will be orbiting through this hazardous zone. The operational costs of shielding them, or the cost of losing them to radiation frying their electronics, will increase. The splitting of the anomaly is particularly intriguing because it confounds our simpler models. It indicates that the fluid dynamics in the core are evolving in ways we cannot perfectly predict. A splitting anomaly suggests a high degree of complexity in the core mantle boundary, the place where the molten core meets the solid mantle. It shows us that the field is not just fading away, it is tearing itself apart and reassembling. This leads us to the inevitable question of what is driving this. We have the pole sprinting north, we have the field collapsing in the south. These are not isolated incidents, they are connected symptoms of a single massive engine. To understand why the shield is failing in the Atlantic and moving in the Arctic, we have to look deeper. We have to look past the crust, past the solid mantle, and into the churning, superheated ocean of metal that lies at the center of our world. The changes we see in the sky and on our compasses are merely echoes of a storm raging more than 3,000 kilometers beneath our feet. That is where the true story of Earth's magnetic evolution is being written. We have looked at the symptoms, the racing pole, and the expanding anomaly. Now we must descend into the cause. The source of Earth's magnetic field is a mechanism known as the geodynamo. It is located in the outer core, a layer of molten iron and nickel that is roughly 2,200 kilometers thick. This is a violently deep environment, deeper than the deepest ocean trench or the deepest mine. Here, temperatures rival the surface of the sun and the pressure is immense. The iron is fluid, having the viscosity of water, and it is in constant turbulent motion. The magnetic field is not a permanent magnet like the one on your refrigerator. It is an electromagnet. It is generated by the movement of electrically charged fluid. As the liquid iron flows, it generates electric currents, and those electric currents in turn create the magnetic field. This is a self-sustaining feedback loop. The heat from the solid inner core drives convection currents in the liquid outer core. Hot iron rises, cools, and sinks again. At the same time, the rotation of the Earth spins these rising and sinking columns of metal into spirals. This complex, twisting flow of conductive fluid is the engine that powers our planetary shield. What we are witnessing right now, the acceleration of the North Pole and the deepening South Atlantic anomaly, indicates that this engine is stuttering. The flow of iron is changing. It is becoming more turbulent. Imagine a smooth-flowing river that suddenly hits a patch of rapids. The water churns, eddies form, and the flow becomes chaotic. That is what seems to be happening in the outer core. We cannot see the core directly. It is inaccessible to any probe or camera. We can only infer its behavior through indirect measurements. We use satellites to map the magnetic field at the surface and then use complex mathematical models to project those field lines downward to the core mantle boundary. What these models reveal is fascinating. They show recently formed patches of concentrated magnetic flux moving around. Specifically, there are high-latitude lobes of magnetic flux centered over Canada and Siberia. For a long time, the Canadian lobe was stronger, keeping the magnetic pole anchored in North America. But in recent decades, the Canadian lobe has weakened and elongated while the Siberian lobe has maintained its strength. This imbalance is winning the tug-of-war, pulling the magnetic pole rapidly toward Siberia. This change in the flux lobes is caused by a jet of molten iron. We have detected a stream of liquid metal moving within the core at speeds that are high by geological standards. This jet is altering the magnetic landscape deep below, sweeping the magnetic field lines along with it. It is this fluid motion that dictates the surface changes. The magnetic field is essentially tethered to the fluid. When the fluid moves, the field moves. The growing turbulence helps explain the South Atlantic anomaly as well. The reverse flux patch I mentioned earlier, the eddy flowing against the main current, is a result of these complex convective storms in the core. The geodynamo is not a steady, perfectly symmetrical machine. It is messy. It is prone to fluctuations, and right now it seems to be in a phase of high variability. We are watching a planetary-scale system evolve before our eyes, something previous civilizations could never do. We have the unique privilege of seeing the geodynamo in action. But what we see is not perfect stability. It is continuous motion, gradual weakening, and growing complexity. The turbulence we detect could be a temporary weather pattern in the core, a storm that will blow over in a few centuries, or it could be the onset of a structural shift in how the core operates. The core is cooling over billions of years. As the inner core freezes and grows, it releases heat and light elements that drive the convection in the outer core. This process is the lifeblood of the magnetic field. But the efficiency of this dynamo can vary. There are times when the field is strong and dipolar, with two clear poles, and there are times when it becomes multipolar, weak, and chaotic. The current data, with the splitting anomaly and the racing pole, hints that we might be moving away from a simple, strong dipole state toward a more complex, multipolar configuration. This brings us to the ultimate question that hangs over all this data. We know the field is weakening, we know the poles are moving, we know the engine is turbulent. Does this mean the engine is about to flip? Are we seeing the early warning signs of a full geomagnetic reversal? To answer that, we have to look away from the computer models and look at the rocks. The geological record holds the history of the magnetic field, and it tells us that what is happening now has happened before, often with dramatic consequences. This leads us to the topic of reversals and whether we are overdue for one. Given what we now understand about the turbulent engine beneath our feet, the possibility of a geomagnetic reversal becomes a very real subject of inquiry. A reversal is not a disaster movie myth. It is a proven geological fact. We know for certain that Earth's magnetic field has flipped its polarity hundreds of times over the planet's history. North becomes south, and south becomes north. The compass needle that points to the Arctic today would have pointed to the Antarctic a million years ago. The last major reversal happened about 780,000 years ago. It is known as the Brunhes-Matuyama reversal. Since then, the polarity has remained relatively stable. However, stable is a relative term. The intervals between reversals are highly irregular. Sometimes they happen every 200,000 years. Sometimes they wait for millions of years. The fact that it has been nearly 800,000 years since the last one leads some observers to suggest that we are overdue. In geological terms, we are in a long stretch of stability that is statistically likely to end. When a reversal occurs, it does not happen overnight. It is a slow, chaotic process that can take thousands of years to complete. During a reversal, the dipole component of the magnetic field, the simple two-pole structure, collapses. the field strength drops dramatically, perhaps to 10% or less of its current value. As the main field fades, the magnetic structure becomes complex and multipolar. Instead of one North Pole and one South Pole, the Earth might have multiple weak poles popping up in different places. A North Pole over Africa, another over the Pacific, a South Pole near the equator. A compass would correspond to nothing useful. The protective shield would inevitably be weak and fractured. Rock layers from ancient periods preserve the orientation of magnetic minerals, acting like frozen compasses from the past. These records reveal that before a reversal, the field often exhibits the exact symptoms we are seeing today: a sharp decrease in intensity and rapid movement of the poles. We are seeing a 10% drop in 2 centuries. We are seeing the pole sprint. We are seeing anomalies grow. The pattern recognition is difficult to ignore. However, science demands caution. Not every excursion leads to a full reversal. There are events known as geomagnetic excursions, aborted reversals. During an excursion, the field weakens and the poles wander toward the equator, but then the geodynamo rights itself and the poles snap back to their original positions. These are actually more common than full reversals. The Lachamp event, which occurred about 41,000 years ago, was a brief excursion where the field weakened significantly and the poles shifted, but a full reversal did not stick. Is the modern data pointing to a full reversal, or just an excursion, or simply a large fluctuation? The honest answer is that we do not know yet. The timescales are the problem. We have precise satellite data for only a few decades and reliable navigational data for a few centuries. A reversal process unfolds over millennia. We are trying to predict the outcome of a marathon by watching the first few steps of the runner. Some studies suggest that these transitions were accompanied by increased radiation exposure and environmental stress. If the field weakened significantly for 1,000 years, the ozone layer could be damaged by solar particles, altering the climate and increasing ultraviolet radiation at the surface. Life has survived many reversals, so it is clearly not an extinction-level event for biology. But for a technological civilization, the stakes are different. We must consider the possibility that we are living through the early stages of a significant magnetic event. Whether it is a reversal or a deep excursion, the trend is toward a weaker, more complex field. This brings us to the final and most practical part of this deep dive. What does a weakening, shifting magnetic field mean for us right now? How resilient is our modern world to prolonged magnetic instability? The Earth is changing, and our technology is sitting squarely in the path of that change. Modern civilization is built on the assumption of stability. We build our cities on ground we assume will not shake, and we build our technologies on a magnetic foundation we assume will not change. But as we have established, the magnetic foundation is changing. The accelerating drift, the South Atlantic anomaly, and the turbulence in the core all point to a more dynamic system than we planned for. The question is, can our grid handle it? Aviation and marine navigation are the first to feel the shift. While GPS is the primary tool for location, magnetic compasses are still the critical backup for orientation. Every commercial aircraft, every cargo ship, and every military vessel relies on accurate magnetic data. As the pole moves, the world magnetic model must be updated rapidly to ensure these backup systems do not drift into error. Airports are already physically repainting their runways. A runway named 27 implies a magnetic heading of 270 degrees. If the pole shifts enough, that heading changes, and the runway must be renamed 26 or 28. This is a minor administrative cost, but it symbolizes a larger truth. The map is no longer fixed. The greater danger lies in the weakening of the field. A weaker magnetic shield means less protection from solar storms. When the sun erupts with a coronal mass ejection, it sends a wave of charged particles slamming into Earth. A strong magnetic field deflects most of this energy. A weak field lets more of it through. These geomagnetic storms can induce electric currents in long conductors on the ground. Specifically, our power grids, transformers, can overheat and melt. In a world dependent on electricity for water, heat, communication, and finance, a grid collapse is a catastrophic scenario. As the field weakens by 10%, 20%, or more, our vulnerability to even moderate solar storms increases. We are lowering our defenses at the exact moment our reliance on delicate electronics is at its peak. Satellites are the backbone of the modern economy. They provide the timing signals for stock markets, the GPS for logistics, and the data for weather forecasting. They are especially sensitive to radiation. As the South Atlantic anomaly expands, satellites face higher risks of degradation. If the field continues to weaken globally, the kill zone for satellites expands. Losing key parts of our orbital infrastructure would not just mean no GPS on your phone. It could mean a breakdown in global supply chains and financial synchronization. Radiation also impacts the atmosphere. High-energy particles penetrating deeper can alter the chemistry of the upper atmosphere, potentially depleting the ozone layer. This would increase UV radiation at the surface, which has long-term health implications for humans and ecosystems. We are not talking about immediate disaster, but a slow, creeping stress on the biological and technological systems that sustain us. Despite this, public attention remains minimal. The changes happen on timescales that are too slow for the 24-hour news cycle, but too fast for geological comfort. We are watching a slow-motion transformation. We need to understand that the Earth is not a dead rock. It is a living, breathing, dynamic system driven by immense forces far beyond human control. Its magnetic shield, essential for life as we know it, is not fixed. It moves, it fluctuates, it weakens and strengthens, and right now it is changing in ways that scientists are only beginning to fully grasp. Perhaps these changes will stabilize. Perhaps the pole will slow down and the anomaly will heal. Or perhaps they mark the early stages of a transformation that will reshape the invisible environment around our planet over the next few centuries. We do not yet know the destination. What we do know is that the shield protecting Earth is not permanent, not static, and not guaranteed. It is evolving, and so quietly is the future of life and technology beneath it. If you found this deep dive into Earth's changing magnetic field valuable, please leave a like on this video. It helps the algorithm share this scientific analysis with more people. Stay curious, stay informed, and remember that the ground beneath your feet is more active than you think.